So we've been working on integration. What I want to do is just kind of do a quick practice problems and make sure that we have some different perspectives in place of what to expect from different rules. But we also need to talk about substitution. I know I kind of briefly introduced it to show where some of the rules come from, but we can use it for more than just, hey, this is why it's helpful. Okay. And what we'll see here with these two, I've given it in some different forms. Both of them are considered definite integrals, though, here, because we have a lower bound and upper bound on this integral that was given. And over here, we're given a boundary value here that we want to use in an interval from -2 to 4, okay? Now, things to make sure you remember here, always double check to make sure your function's continuous over these boundaries, which kind of give it away for the most part, like for a final exam purpose. If we're asking you to evaluate the integral, it better be continuous. Okay, if this was Calc 1 for the science majors, even then, probably is going to be continuous. Okay, but always make sure you're paying attention to that. Now, for the first one here, are we good if I write 2 times x squared over 2 for the antiderivative portion? Any concerns with that? Now, if you wrote just x squared there, is it wrong? All right, so if you don't need to see the fraction the way I've written here, please remember, just put x squared, okay? I'm just making sure to show you like, hey, we left the 2 alone. The antiderivative of x is increase the exponent by 1 divided by the result. Here, we definitely like to use brackets, though, to help make sure to keep those boundary values in place, because our next step here, once we have it simplified, is to use that fundamental theorem of calculus, 3 squared minus 1 squared, which will give us what, 8? So the area under the curve for this situation gives us just 8. Now, what could we do to kind of confirm this one? Is that, make sure you see it, that's a linear function, right, that we're working with. So if we wanted to, we go back and use some geometry, okay? It's kind of going through, remember, I kind of quickly drew one yesterday before we moved on. Any concerns with that process, though? All right. Do we feel okay with setting up an integral ourselves when we need to? One thing I would point out, like if you need to, I believe I uploaded some videos from my online class, y'all's class, if I recall correctly, that go into a little bit more about the properties of integrals. That can be helpful sometimes. I don't feel it's like necessary, but it can be a helpful perspective. So those should be in the modules if you need that different perspective. Okay. If you ever get stuck on a problem assignments, as always, just make sure you contact me. I'm going to do my best to sit down tomorrow and work on a practice or kind of review thing for the final. Because when I was going through my files from the springtime, I thought I had made something. I have no clue where I put it. So if I could find it, I'll share it. If not, I'll do my best to kind of put one out there, kind of like what we did for some of the exams. Okay. But if I go through with this one, are we good with where I'm getting this antiderivative from? Concerns there? Now, the one thing to hear, always be careful with your exponential ones. Kind of given the time frame that we had for some of this stuff, I didn't go into all the details. Everything we really focus on is base E. So sometimes it can change depending on, like, say you had 2 to the x, okay? So there are some things that can affect that. Now, the other thing I would say here is watch out. What if I had something like e to the 3x, right? So remember, that's where that chain rule perspective we have to watch for. Okay, here I had just e to the x, though. With that said, though, we'll have 12 plus e to the 4th minus -6 e to the -2, sorry, plus e to the -2. Which you're not going to be able to do much more with that just because the e's are not like terms. I know sometimes assignments on homework might write stuff differently, but just make sure you see here, this is probably the best we're going to get it. There we go with where I'm getting that from though. Any questions, concerns though with just kind of some of these different rules? I got some other ones that we're going to walk through as well. All right. So as we see here again, just kind of making sure we handle different situations. It can be given to you as a definite interval already set up. Make sure you're comfortable setting it up yourself if they give you the interval to start with rather than the integral. Okay. Also know here we were just trying to find the area under the curve. So that was a very specific purpose we were dealing with. Anybody need this still though before we go to the next problems?
Right. That's
All right. So the other thing I wanted to make sure to go back to is just don't forget about some of the different problems we have. So yes, Monday and stuff, we started focusing more on the definite integral aspects. But here's a problem: says, hey, we have an air conditioning company that determines the marginal cost, right, for the X air conditioners given by this function. Okay. Now keep in mind that sometimes you want to watch for these types of statements. Is that for the marginal cost or the cost function? That's the cost function, right? So that doesn't go with this function here. That's going to go with the cost function. So what you're seeing here is they're giving us an initial value. Now, this piece here is really why we call it the initial value. Okay. What do we do then to get from marginal cost up to the cost function? Okay. Now, as far as notation is concerned, make sure you remember, hey, I'm starting with the derivative. So if I want to get up to the cost function, I need the antiderivative. So a great way to write that is, hey, c of x will equal the integral or the indefinite integral of my marginal cost. Okay. Different functions that you might want to be comfortable with here is not just marginal cost. I don't think we've looked at it for a couple of weeks, but don't forget that you could have something like an acceleration function. Well, if you integrate the acceleration function, you're going to get the velocity function, right? So acceleration goes up to velocity. One thing we definitely looked at is the derivative of the velocity function is the acceleration function. So make sure that you're connecting some of those, right? The distance function, position function would be connecting that with velocity. So we're just seeing here that same kind of relationship with marginal cost and cost. Now, the one reason I definitely wanted to go over this one is when I go through this problem here, what can I not forget with my antidrift? So when I go write this here, remember we divided that by 2, so that's why I dropped it down, just like that first problem we did. What do I need to have here when I do the antidrift? The constant term, right? Now, technically here, you'd get away with it if you forgot, to be honest with you, okay? But in your work, it's better to put it until you can show why you don't need it, okay? What the idea here is the reason you get away if you forget it. Well, C of 0 is 0, so that means my constant term needs to be 0, okay? So the actual function that we're looking for will be the C of X equals negative 0.1x squared plus 500x. Okay. But that's a situation where, hey, now that I'm dealing with something that's not a definite integral, I'm not trying to find the area under the curve or all these different perspectives that can come with it. I just want the function itself. Don't forget about your constant term. Okay. The nice thing about the initial value is, though, they're telling you what your constant term should be. But we've also looked at some like where I could have done something like, hey, C of 5 is 200, right? Just kind of throwing something random out there. Okay. Well, with air conditioners, based on my experience, it'd be more like 25,000 instead of 200. But be careful to see the difference between the initial value and then just some other point of reference. Everyone follow me on that? Any concerns or questions with this one? And remember, if you get stuck and you're not sure when to put plus C or not, you could always put plus C because when you do a definite integral, a constant term minus itself will always go away anyways. So the kind of the work will get rid of it. It's just extra work you don't want to have to do. Okay. Questions? All right. So these last two are some of the integrals that we run into some issues when we try to work them out. Okay. We don't have any rules that this is how we handle this problem. So we have to have other ways to deal with it. Okay. Now, what I'm about to show you is not always going to work. All right. But one area where we've seen this is that e to the 3x situation here earlier. Okay. If we just take the example of using a derivative of e to the 3x, remember we would have e to the 3x times the derivative of that exponent. The chain rule is involved. That's a big part of, always watching when we're dealing with derivatives, watch out for that chain rule. Well, guess what? With integrals, sometimes we can use that to help us evaluate the integral itself. Okay. What you'll find here, though, we're going to connect back to that was like e to the u of x. So it would be e to the u of x times the derivative of that. Okay. So I think I kind of briefly mentioned it when we first started integration, just kind of show you where the rule comes from. But remember, that's where we're connecting back to is this whole idea of the u of x and the derivative of u of x. Okay. So what you're going to find here is u substitution is typically what's used by most people. Okay. First and foremost, so make sure you see here, we don't have any rules for something that looks like this. So when it comes to integration, if we can use a rule, that's awesome. But when we can't, okay, we have to have other techniques in place. Okay. One of those techniques in place is where substitution comes in. All right. What that requires from you, though, is to say, hey, what are some ways that I connect these two together if I think of it from a derivative perspective? Okay. So as you look at these two expressions, what stands out to someone from like if I took a derivative of them separately, not the whole thing, but separately to the derivatives? So if I just kind of write this out just for exploring purposes, what's the derivative of 2x? 2. Doesn't really help us too much, right? What's the derivative, though, of x squared minus 3? What stands out to you about that, though? That's the numerator, right? And so if we can find a way to connect this stuff, hey, that might help me a little bit, right? There's some type of connection. Well, what you're going to find here is we can say that our focus here is u equals that denominator. Oops, not 2x, sorry. Now, my notation is definitely going to get sloppy here, but what you're going to do is, hey, let's differentiate this with respect to x. Because we're really focused on x. We're just using u as a placeholder. Down here, we typically use the u of x, but we're just kind of shortening it to say, hey, we're going to call this u. Okay, just kind of make it easier to work with. Now, technically, we're supposed to write du dx equals 2x, right? But remember, this came from us looking at that difference quotient where it was a change in y over the change of x. So there's some division going on here, okay? So to help simplify this work a little bit, we're just going to multiply this over here to this side, okay? Now, the reason we're doing that is I want to set up an integral I can evaluate. Okay, so that's why I say it's kind of sloppy notation, but when we use it, it's going to help us out. Okay, specifically, what we're saying is instead of writing this, what letter are we going to put in its place?
You.
It helps make the denominator a lot easier to work with. Does everyone see what I'm doing here? So that we can come over here and say, hey, I'm just going to call this something over u. Now, in order to do that, if I want to deal with this, I have to deal with this here. We can't have two different variables going on when we're dealing with our integral right now. Okay, we're not doing three-dimensional stuff here where we have that set up. This is very specific. I want to keep it with respect to the fact that that was all x to start with. Well, that's where the derivative helps us at, because what do you see in this statement that we can use? Well, hey, there's that dx, right? Well, what's right next to the dx? The 2x, the other piece of the problem that I have here, right? So what they're saying is from our derivative, if I want to put du here, what must I have in my original problem?
2x.
2x and the dx, right? Well, guess what? Don't we have that? So what we're seeing here is, hey, I can substitute that piece in as well. Just as I put u for 2x squared, I keep saying that. As we just put u in for this x cubed, x squared minus 3, we can plug this in for that piece there, right? So I'll just put this as 1 over u du.
Somehow they all related to each other.
Mm-hmm. And then what we're taking advantage of is that fact that, like, hey, sometimes the way derivatives work, you're going to have a chain rule take place, and this is us undoing the chain. Is that always going to work, though? No, all I have to do is go change this to something like x cubed, and all of a sudden it doesn't work because I don't want x cubed, I want just x, right? In the same way, if I change this to x cubed, it still won't work out because that would put an x squared somewhere that I don't have an x squared, right? So this only works with specific situations, okay? So sometimes you'll find here, it's kind of a guess and check. Let me see if it works. If it doesn't, well, I need to do something different. The good news is for our class, when you get to this situation that it doesn't follow a direct rule, substitution is probably going to work on the final. Everyone follow me on that? The main thing I want you to see this though, as we're practicing and connecting to it, hey, this is us just going back over the chain. Okay, that's kind of the focus here. Now, with that said, the nice thing about this new integral is that follows a rule we should be familiar with, right? What is the antiderivative if you have 1 over your variable? The natural log, right? Now, be careful here. This is going to be where we definitely want an absolute value because I didn't give us any like domain restrictions here. I'm not going to go in too much details, but just make sure you see that. And then, hey, we have our constant. With that said, though, do I want u? No, we need x, right? So make sure you go back and say, hey, I did all that just to be able to work it out, but let me put this back in place. Okay. Now, I guess I could have put it as x squared plus 3. That would help. We wouldn't need the absolute value. Remember, I think we looked at one of these the other day where it's like, hey, you don't need the absolute value in this situation. Well, here, technically we do because 1 minus 3 is negative 2. We don't want that. So we have to be careful, okay? I'll make sure on my part, when I'm putting together the final, that if you put the absolute value, good. If not, we can talk more about that later kind of thing, okay? But one thing I do want to make sure to show you here is if I take this piece here and I take a derivative of that, I'm going to put it as parentheses right now for the sake of making that as straightforward of a derivative as possible. Okay. What is the derivative of any constant term? 0, right? So is everyone good with that? If I just get rid of that right now? What is the derivative of a natural log? So there's different ways to remember it, right? So if you have it that way, that's perfectly fine, right? But the key is it's 1 over the argument times the derivative of that argument, the piece that was on the inside. Okay, so if you have it memorized that way, nothing's wrong with that, okay? But make sure you see there, hey, that gives us 2x over x squared minus 3. So did we do our integration correctly here, our antiderivative? Well, hey, isn't that exactly what we started with up here? That's the good news about like the final exam. If it's a 2-hour test, right? For this class, I feel like you do have some time flexibility on this test. It's not like college algebra where you probably were taking it for the full 2 hours. This one might be more 1.5 hours. Okay. If you have the time, though, go to your integrals. Let me take the derivative real quick and just make sure I did it correct. Okay. Not all of them are going to require substitution, though, so please keep that in mind. That's why I'm okay just doing a couple examples with y'all. If you need more help after the homework, just as I mentioned, reach out to me, okay?
How many questions do you find out?
How many do you want?
Question.
How many do you want? You want more or less? The main thing I'm going to tell you is it's going to take you about 1.5 hours. Okay. Some of the questions like this here, I can see someone being comfortable. Like I see what the answer is right now. Make sure you show your work though. Okay. As mentioned, it's like the derivative aspect. There are some things that people like some of y'all don't do this on the test, and that's perfectly fine. Okay. Because as long as you use your chain rule, I'm fine with that and we're consistent with it. Okay. So for what I saw in the spring, it was about 1.5 hours. Okay. I usually adjust problems though, because there was a couple, like say multiple choice problems. I may not have said it the same way another teacher said it. Okay, but hopefully you'll see from the practice, there's some definitions that we have to make sure go back and review. We haven't talked about. I've used them for the purpose of explaining something, but not the technical definition the book gives. So there's a couple of them that's why I want to get that practice out as soon as possible. Okay. I'll do my best though to get it done Friday or Saturday. No promises, but I'm going to do my best. Was there any questions though before we go to the next one? All right, so the next one here, definitely a little bit more going on. Okay. What you'll see here is that of division, I'm multiplying two things together. Those will be kind of good hints that you might need substitution somewhere. Not addition and subtraction where I could just break it up. But multiplication and division, I might need to do something here to work it out. Okay. Another one where you might be forced into substitution is like if you're given something like this. A radical, right? Because we can't really deal with it. So no, like if you have a square root involved, that would be a cube root involved. Make sure you watch out for those. That's probably a hint that I might need substitution here. Okay. But also notice the denominator here was x squared, right? What does this exponent have that I have to be watchful for? An x cubed, right? So that's kind of your hint that doesn't follow the rule that we were given, right? The rule that we're given is that e to the ax dx equals 1 over a e to the ax plus c. That was the rule we are given. A constant multiple of a variable, not x cubed. Okay. Now, with that said, though, since we're being forced into substitution here, what would someone set u equal to? All right. X cubed would be considered the inside part of this function, right? Kind of following the chain rule idea. What's on the inside? Well, that exponent's the part that's kind of held there in place. What do you like about the derivative of this? Bring down the 3, subtract 1, right? Now be careful here, our sloppy notation. We're using kind of implicit differentiation in a sense too. What should I put behind my 3x squared?
Yeah.
Dx, right? Technically it's du dx equals that, but we know why we're using it here, right? It's to help me do this interval. Okay. Now, Over here, that means we'll putting e to the u, right? Does this help us here for that whenever we look at this piece? That's exactly what we have, right? So substitution, that's nice, okay? So we'll see over here that I can go rewrite this one as e to the u du, okay? However, be very careful, what did I not put on my new integral? The 5 and the 1, right? The interval we were given was x needs to be on the interval 1 to 5, right? When I go from here to here, we're no longer using x, we're going to use the variable u, okay? I didn't do that over here though, because this was an indefinite interval, right? It was just the purpose of finding an antiderivative. This is an example where, hey, if I have a definite interval, I need to be careful with that. I don't want to just copy down the 1 and 5. One thing you can do, go plug it in. Say like, hey, UB would be 5 cubed and UA would be 1 cubed. That's fine if you want to just stick with U the rest of the way. But know that you could also take the approach we did here, right? Do it, then plug X back in. But be careful with what you write. I would encourage you to take this approach. That like, hey, since I'm going from from X to U, let me make sure to change these based on the statement that I just gave. So that's what you're seeing here, why I cubed the 5 and cubed the 1. So 1 cubed, hey, we're still going to be using 1. 5 cubed, however, is what, 125? When you have a definite interval situation, that's going to help save some work for you on the back end when it works out nicely. Okay. It's not guaranteed to work out nicely though, because you might get something with a natural log or something, because different things you can run into is like, hey, if I use u equals the natural log of x, du then is 1 over x. That might work for you trying to work a problem out. You never know. Oops, forgot my dx. That's not going to be necessarily the nicest thing to plug into. Okay, so that's why I say just kind of pay attention. You forget, no big deal. But what we'll see here is that would give us what, e to the u from 1 to 125. So e to the 125 minus e. Keep in mind, I just made this up so for that specific instance. Questions, concerns with this one? Do we feel okay with this when it's nice? Like the nice thing about these, of course, is, hey, that's exactly what I was looking for. Is everyone feeling good with that? Do we feel okay with where I'm getting the 125 and the 1 from here? And me using the subscripts here just makes you remember it's still B and A, right? It's my upper bound and my lower bound, but I'm just making sure to show that, hey, it's because I went to U now that I'm using that different notation. Okay. Are there any concerns though before I try to do one more problem? I want to do one more just to make sure to show that it sometimes we can have wiggle room. Okay.
What is the third step? The u equals,
So remember, this was allowing us to do the integral, right?
okay,
But because it has boundary values, we're trying to do a definite interval. I'm going from x to u, so I needed to change x equals 5 and x equals 1 to u values. That's what that is right there. So I just used this statement here. That's why I was like, hey, just cube the 5, cube the 1 as you go. Okay. Now keep in mind, you're not always going to have to do that because you might have just an indefinite interval, right? But here I had those boundary values. Okay. Does that help?
yeah.
Now, as I mentioned, those were nice because the substitution was pretty clear. Like, hey, that's exactly what I was looking for. Let's look at one that may not be as direct. Go ahead and do one of the radicals too. Just make sure we have that example. Now, hopefully you saw too, another one to watch was those natural logs, okay? Because then u equal the natural log gives you 1/x. That might help you out sometimes. Just careful your chain rule because that might be a part of it too. Working that out, okay? Now, it's nice when you catch and see those things right away that are helpful, but sometimes just trying it out to see what would happen is also an approach that you'll want to take. What you'll deal with this one here is, hey, let's go for what's inside the square root. Let's target that first, okay? Once I take the derivative of this, though, what stands out to somebody? All right, so we have our dx, right? So we're good there. What else does it have that we needed? Well, the three's gone, right? This part, remember, that whole piece here is for this, so we're good there. So we're going on to, hey, we need to, I got that taken care of, so it's this piece we have to take care of. Okay. So as you look at this over here, we have the dx, right? What else do we have that we can use? That we needed, I should say.
Dx.
We got the dx highlighted, right? Do we have an x though over there? Yeah, does everyone see we have the x and dx? So what's the only thing that's not working out nicely? What is over here that's not over here for me to use that I need? The 10, right? Does everyone see that? That, hey, I had an x and a dx. That's awesome. Well, for a number, that will not keep you from dealing with the integral. Okay. So what you'll do there is like, hey, if it's only the value that's messing you up is that number, a great way to rewrite this problem is to say, hey, let me go over here and say, I have this in place, right? I have my x dx. What I want to have here is a 10. Okay. Well, if you want to put a 10 somewhere that it wasn't before through multiplication, remember we have what we call, multiplicative inverses. Specifically, what we're thinking is, hey, 10 over 10 equals what? 1, right? So we get stuff like, hey, 10 times 1/10 is 1, or 1/10 times 10 is 1, right? We're taking advantage of that. So if I need a 10 on the outside, on the inside, sorry, all I need to put is a 1/10 on the outside. So if it's a coefficient, just a number that's making it to where the substitution doesn't directly work, we can fix that. Okay. Just make sure you see here, I'm putting this 10 on the inside so that it matches up exactly for what we need. Okay. I'm putting this on the outside though, because we did not have 10 to start with. There was no 10. So, hey, 1/10 times 10, well, that's 1. So I'm not really changing it. I'm just making it to where it works better for me. Okay. What we'll have at that point then is, hey, this can be written as 1/10 the square root of u du. Pointing back again to the fact like this is what we were using for u. So that's where that comes from. And with that 10 in place, that now matches this, so I can put du there instead. Things that we do kind of oftentimes like solve, like, hey, add this to both sides, subtract this from both sides, but just a different way to use it. That comes up sometimes.
I didn't understand how we bring back the 10 to the equation.
It wasn't there, right?
Yeah.
So I put it there. Am I allowed to do that? Just put something there?
Yeah. Then
As long as I have that, right? But the key is to go back to why I wrote all this. all of that equals what? So did I change the problem? If I go in there and I just put a 10 there, that's definitely changing the problem, right? If you just try to stick a 10 in there, you can't do that.
Basically, just put one.
Yeah, so if you need it there, just remember, hey, 1 over whatever I need, and I'm good to go. So the 10 definitely wasn't there, but I needed it. So I put it there. Everyone follow me on that? It's not gonna happen all the time, though. Y'all want some breakfast?
Y'all want some breakfast? It's sausages, pancakes, and eggs. It's free. We're not charging.
I'll take it.
All right.
Now, the one thing here with radicals, just remember, use your 1/2 there, and it goes right to some of the other stuff we're working on, so. Now, y'all gotta come work out a problem for us?
All right, took this class. You have a good one. Thank you.
Y'all have a good one. Now, the one thing I will say, whenever you have radicals, be careful with your integration here, okay? If you need to, again, write it out as we did with some of the other stuff in this form, but just remember that 3/2 in denominator, I'm gonna use a reciprocal. That's the one thing I would say be careful of with this problem. We don't want 3/2 out front because technically we should be dividing by it. That's where the 2/3 is coming from, okay? But that would give us, what, 1/15? So u to the 3/2 over 15 plus c would be our final, antiderivative here. Could have boundary values that change here. I didn't do that with this one. But that's just stuff that to watch out for. So here's our example of, don't forget your rules for radicals, right? But also just know that for substitution, if you need to force it in, you can force a constant value, something that you just multiply by, okay?